Hello everybody, in the previous video we have solved this circuit with the mesh method, let's say. We have found three equations with three unknown variables, so we were able to solve the system and find all the values of currents and voltage of the circuit, which is the goal of the problem, let's say. In this video I will show you how to have the same result with a different method. So we understand mesh, we understand voltage drop and currents, and so we apply another point of view to the same circuit that we can solve it in a faster way. So we have this voltage source, this current I coming into the circuit, which go into R1, and then splits into I1 this way, going this way, and then coming back here, and splits into I1 and I2, which go this way, and then they combine back to the current I. So basically, we can see this network of resistance as an equivalent resistor, an equivalent resistance between these two terminals of the circuit, this thing here and this thing here. Okay, so let's do it. Just delete this symbol. And we have this drawing. So I write here an equivalent resistance, which takes into account all the network. Okay, and I have the same current I coming in this direction, the same in this circuit and this circuit. So the equivalent resistance is equal to, let's see what we have here. We come from this side, we have R1 plus the parallel of R2 with the sum of R3 and R4. So this thing here, R1 plus R2 in parallel with R3 and R4. We changed values here. We see that R1 is 1 kilo ohm, R2 is 1 kilo ohm, in parallel with 500 plus 500 ohm. So 1 kilo ohm here. 1 kilo ohm in parallel with 1 kilo ohm is half kilo ohm. So basically, the equivalent resistance is 1.5 kilo ohm. We know that this resistance is this value. We know the value of the voltage here, so we can find I. And I is actually the same current here. So we just have one variable of the circuit here, which is now a known value. So I have solved here all this, let's say the following equation. So we start with I. I is equal to 9 volt divided 1.5 kilo. So I is actually 6 milliampere. I find I with this simple method. So I have, just because the current here is the same as the current here, because the current that go into this terminal and come back from this terminal. And the equivalent resistance is the resistance between these two terminals. So I have I here, I forget about this circuit, and I come back to my original circuit. I comes into R1 and produce here a voltage drop, which I don't name for not adding more elements to this plot, to this graph. And anyway, I don't write the name here, but I can say that this voltage drop, I name it V1. So V1, the voltage drop here on R1, will be equal to the product of I times R1, which is actually I, 6 milliampere, times 1 kilo ohm, which is R1. So I know that V1 is 6 volt. And I can write this down here. So I can write this down here. I can say here that I have 6 volt. If I have 6 volt here on R1, and I know that this mesh must give me the same, 0 from the algebraic sum of the voltage, I have 9 volt here, I have 6 volt here, I must have on R2 3 volt. 3 volt because 6 plus 3 is 9. You can do this with the mesh as in the previous video, but just look at the mesh. We have 9 volt from this point to this point. We must have 9 volt from this point to this point for the Kirchhoff's law of tension. So we now we know the value of V2. V2 is 3 volt. If you know V2, we can calculate I2. So, because I2 is equal to V2 divided R2. So we know that we do the operation, R2 is 1 kilo ohm, V2 is 3 volt, I2 is 3 milliampere. But actually I2 is And we know that the current I, which is 6 milliampere, divides into I2 and I1. So I1 must be I minus I2, which is also 3 milliampere. So the current just split into two equal parts here due to the values of the network, this resistor network. So I1 is 3 milliampere too. With I1, we can calculate the voltage drop on R3. We call it, let's say, V3. So V3 is equal to 500 ohm, the value of the resistor, times the current flowing to the resistor, which is 1.5 volt. So we can write here this value. Here we have 1.5 volt. And the same argument for the voltage drop in R4. We have 500 ohms time I1, which is the same, 3 milliampere. So we have also 1.5 volt here. 1.5 volt here. So we have now all the values of this mesh. Let's just look at this. We have this 9 volt, which divide into 6 volt here and 3 volt here. And these 3 volt, actually from this point to this point, are also the sum of this 1.5 volt, 1.5 volt. And notice this thing is coherent with the current, which is 6 milliampere here. I can write this here now for being clear. 6 milliampere that flow into this current, produce this voltage drop, then split into 3 milliampere here and 3 milliampere here, and produce here 3 volts and 1.5 volt, which sum up to 3. So all the circuit is coherent, and we can check this actually is correct. This makes sense. I hope this video will help you in solving your problems and exercise, and follow me with the next video if you are interested in this. Thank you for your attention.